Okay, welcome to the channel. Today in this video we are going to discuss about systems of variable mass or the rocket. So we are aware of the conservation of linear momentum. So in conservation of linear momentum we discussed, we said that the applied force is directly proportional to rate of change of momentum dp by dt, where this p is the momentum and mv. So we said f is proportional to change in momentum, so we said mass, this is v1 minus v2 divided by the change in time, that is t2 minus t1. So this is what is force all about. So here we considered the mass to be constant and the change is only in the speed or the velocity of the object, we said. So in case of a variable mass, where we will consider that the mass is changing constantly with respect to time. So what will happen in this case, where the mass is also varying, velocity is varying and the mass is also varying with respect to time. So for example, we will consider the rocket, in which the mass also constantly changing because of the fuel getting burnt and the gas is escaping. So the mass is continuously decreasing with respect to time. So what will happen in this? So there can be two types of fuel used by the rocket. One is solid fuel, or the other option is liquid fuel. If it is liquid fuel, then it can be liquid hydrogen or liquid paraffin. In addition to that, there will be a suitable oxidizer like oxygen, hydrogen peroxide, or nitric acid. Okay, so these two things are stored up in separate chambers, are injected into a combustion chamber where the fuel is burnt. So in case of solid fuel, the fuel itself carries its own oxidizer like gunpowder, and hence a separate chamber for it is not necessary. Only for liquid you will have two chambers required, one for the fuel and the other for the oxidizer. So they are sent to the combustion chamber where the fuel will be burnt and huge amount of gas will come out through the orifice, which is a small opening at the end of the rocket. So it will form a jet or high velocity stream, which is called the jet. As a result, the rocket is propelled forward, since the momentum lost by the jet of the gas must be equal to the momentum gained by the rocket. So because of conservation of momentum, the momentum that is lost by the jet of the gas must be equal to the momentum gained by the rocket. So using this conservation of momentum, then further study. So this you can see an animation shown. So this is the hot gas ejected, the jet ejected out. So here you can see the combustion chamber, and there are two separate chambers, oxidizer and fuel. So oxidizer and fuel come out of this and they are burnt inside the combustion chamber, and then through the orifice hot gas in the form of a jet comes out, and the momentum is given to the rocket and it moves forward. So this is the mechanism based on the Newton's third law. So let us consider capital M is the mass of the rocket, including fuel and oxidizer. Capital V is the velocity of the rocket at any instant of time t in the inertial frame of laboratory. Alpha, the rate of change of mass of rocket, the rate of change of mass of rocket due to the escape of hot gas in the form of a jet. Small v, velocity of the jet of hot gases. So we said alpha is the rate of change of mass. So alpha is given as the rate of change of mass dm by dt. The negative sign is because of the mass is decreasing over time. So these are the variables we are going to use the equation. Assuming the forward velocity of the rocket to be along the same line with the oppositely directed velocity of the jet. So we considered the forward velocity, this is capital V, and the jet is going in this direction, this is small v. So velocity of the jet, if we want to find out from the laboratory frame, then this is minus v, and this is plus v. So this gives us the velocity of the jet in the laboratory frame as capital V minus small v. The rate of change of momentum of the jet coming out of the rocket is given by dm by dt, that is the rate of change of mass multiplied with its velocity capital V minus v. As per Newton's third law of motion, this must be equal to the force acting on the rocket tending it to move it forward. Or else we can say this force is nothing but F is equal to dp by dt, the rate of change of momentum, where we got the mass is varying with respect to time dm by dt, and multiplied with the relative change in velocity, or the velocity of the jet is given to be p minus v from the laboratory frame. So the force acting on the rocket propelling it forward is calculated to be dm by dt capital V minus v, considering the weight of the rocket. So here, if you will consider the weight of the rocket as well, the equation of motion for the rocket moving vertically upward now can be given by d by dt of capital mv, that is d, this is the linear momentum mv of the rocket, m is mass of the rocket at an instant of time, and capital V is also the velocity of the rocket at any instant of time. So d by dt of mv is given by dm by dt v minus v, this term, that is the force acting on the rocket, and then of course the minus mg. So this is with the force which, where I mean it is going upward and the weight is acting downward. So this minus mg component of weight. So if you will open this derivative, we have dm by dt, that is the variation with respect to mass, the variation of mass with respect to time multiplied with this velocity, then m dv by dt. This gives us dm by dt multiplied by v, opening this bracket, minus dm by dt small v minus mg. So these identical two terms got cancelled, and the remaining terms of the equation is given by capital M dv by dt is equal to minus dm by dt into v small b minus mg. This implies dv by dt, d capital V is the velocity of the rocket, dv by dt, this m will come here. So minus dm by m dt small v is the velocity of the jet minus g. Integrating with respect to t, we have integration over dv by dt. So we got integration of dv is v, and then minus small b dm by m dt and dt, this is minus g dt, g is constant, take it out. So v equals to minus v dm by m, integration gives us ln m minus gt plus c, this is the constant of integration for indefinite integral. So since at t, so we need to find out the constant of integration that we used. So here if we need to find out that constant of integration, let us take the put the boundary conditions. Let's take t equals to 0, m is m0, that is the initial mass of the rocket including the fuel and the oxidizer, and the velocity, initial velocity v is equal to v0. We have this v0 is equal to minus v log m0 plus c. So c is equal to v0 plus v log base e m0, that is capital V is equal to minus v log m base e minus gt, plus substituting the value for the constant of integration, which is found to be v0 plus v log m0 base e. So v0 plus v ln m0 by m minus gt. Since the mass of the rocket is m after time t, and since the mass decreases at the rate of alpha, so we have already considered this m0 by m, that is the change in mass with respect to the mass at a given instant of time, and we have already defined alpha as the rate of change of the mass with respect to time. So we can rewrite this we can rewrite this as m equals to m0 minus alpha t. M is the mass after a instant of time t, which is the original mass m0, minus alpha is the rate of change of mass over time multiplied with the time, will give us the mass of the rocket at any instant of time. So original mass minus the rate of change of mass over time into time. So for what time the fuel is burnt and came out. So that is m equals to m0, taking common we can write in this form 1 minus this is alpha divided by m0 into t. So this alpha is the rate of change of mass over time dm by dt. So substituting this alpha by m0 by some other denoting it by some other factor beta, we can finally write capital M is equal to m0 multiplied with 1 minus beta here. So beta we wrote for alpha divided by m0, right? So finally the velocity of the rocket at any instant of time, can be written as v0, the initial velocity, plus v small v, that is the velocity of the jet, ln 1 minus beta t. Beta is alpha by m0 time t minus gt. Now here in this you can see this gt also will play an important role. So let us see what will happen if t is very large and t is very small. So this is the equation we obtained. V is equal to v0 plus v log base e 1 minus beta t minus gt. So in case t is small, then minus gt hardly makes any difference because t is very small, we can ignore this term. If t is very large, then minus gt becomes large. The fuel burns at a slower rate. Of course, if this gt will be large enough, then your v will be less. So the ascent of the rocket slows down. The exhaust velocity depends upon the design of the nozzle and also upon the temperature and pressure developed inside the combustion chamber. So temperature and pressure will also play an important role here. The highest theoretical value possible being the root mean square velocity of the gas molecules at the temperature prevailing in the combustion chamber. So here we said, as we know from kinetic theory of gases, that is the average energy per molecule, which is given by E bar is equal to 3 by 2 kb, which is Boltzmann constant multiplied with the absolute temperature. Here this E bar is actually half mc bar square, where the c bar is nothing but the root mean square velocity of the molecules. So the highest theoretical value possible being the root mean square velocity of the gas molecules at the temperature. So here the temperature can be calculated, and practically it will not exceed 3000 degree Celsius. The practical limit to the value of the exhaust velocity works out to be 2 km per second. So if you will consider this temperature T as 3000 degree Celsius, then the value of c bar, that is the root mean square velocity, the velocity is calculated to be 2 km per second, the exhaust velocity. The ratio m0 by m can at least be 10%, can at best be 10% of the initial value m0. M0 is the initial mass of the rocket and m is after some time t. With an exhaust velocity of 2 km per second, initial velocity v0 of the rocket considered to be 0, and the ratio m0 by m as 10, the velocity of the rocket was calculated to be around 4.6052 km per second. So now this value of 4.6052 km per second, the speed of the rocket is very less as compared to the escape velocity required for the rocket to escape the gravitational pull of Earth. So this is what we said 11.2 km per second is the required velocity escaping the gravitational field of Earth, and 8 km per second is the required velocity to orbit around Earth. So both these values, you will see the value that is calculated as 4.6052 is less than 11.2 and very less than 8 kilometer per second as well. So with the exhaust velocity v as 2 kilometer per second, exhaust velocity, in order that a rocket may attain a velocity that is equal to the escape velocity 11.2 kilometer per second. If we will take this velocity, exhaust velocity as 2 kilometer per second, and the velocity of the rocket that is needed to be is 11.2 kilometer per second, then you calculate the mass ratio, which must be 270 or greater than that, because we have not considered the air resistance. So if we consider the air resistance, then it should be little more than 270, this ratio. In the present stage of development, no single stage rocket is capable of such performance. So therefore we have to use multi-stage rockets, 2 or 3 stage rocket, to achieve the purpose. Thank you.